capacitors and capacitance. That is, and then we are going to see the combination of capacitors in series and parallel. Now see in diagram, this is very easy concept to understand. The conductors, that is the first and second shown in the diagram, have the charges positive Q and minus Q with the potential difference, that is the V is equal to V1 minus V2 between them. See in this diagram, this is the potential of this first charge, that is the V1, and the potential difference of the second charge, that is the V2, and the potential difference is given, that is the potential difference is V is equal to V1 minus V2. The electric field in the region between them is proportional to the charges Q. The potential difference V is the work done to carry a unit positive test charge. What is this test charge? It is a small charge from conductor 2 to this conductor 2 to conductor 1 against the field, and at this work done will be proportional to Q, that is V is directly proportional to this charge Q, and the Q divided by V is constant, and this constant term is called as the capacitance of the conductor, that is the capacitor. The constant C is called the capacitance of the capacitor, which depends on the size, shape and separation of the system of two conductors. And then see the SI unit of this capacitance, that is the farad, and the dimension formula is, that is the m raised to 1, l raised to minus 2, t raised to 4, and this is the area square. Again we have the formula for this, that is the 1 farad is equal to 1 coulomb divided by 1 volt. How this formula? That is the Q divided by V. This is the charge, that is the coulomb, and this is the voltage, that is the V volt. This the capacitance or this arrangement is nothing but the one there is the positive charge, another is the negative charge. This combo is called as the capacitor. Now see series and parallel combination of this capacitor. Now see in diagram, this is the principle. First of all we are going to see what is the principle of this capacitor. Let us consider this P1 having an area A. Let some positive charge that is the plus Q is given to the plate, to this plate, and hence potential becomes, for the capacitance 1, this potential becomes, that is the C1 is equal to Q divided by V. The induced negative charges, because of this positive charge, the induced charge is negative. This charge lowers the potential of P1, while the induced positive charge raises its potential. If V1 is the potential on plate P2 due to charge minus Q1, then the net potential of the system will now be, that is the positive V minus V1. This is all this from this diagram. This is the P1, that is the first capacitor, this is first conductor, this is the P2. Okay, plate 1, plate P for plate 1, plate 2. Okay, then hence the capacity C2 is equal to Q upon V. For this C2, this V is V minus V2. Therefore, here this equation becomes, that is the capacity of this second C2 is equal to Q divided by V minus V2. Therefore, C2 is greater than V1. Thus, the capacity from this equation, that is the C1 is equal to Q divided by V and C2 is equal to Q divided by V minus V2. From this, we can conclude that the capacity of metal plate P1 is increased by placing an identical earth connected metal plate P2 near it. In this way, we see this concept, that is the principle of capacitor. Now see, this is the first combination of capacitor, that is in series combination. When several capacitors connected and then the capacitors are said to be series, like this. This is the first capacitor. Now you understood what is the capacitor. Capacitor is nothing but the two positive negative plates connected with each other like this, and these are the first capacitor. This full diagram or this portion, that is called as the capacitor first, this is capacitor second, and this one is the capacitor, that was third one. This, this is, these are in series. Okay. Then in series arrangement, the second plate of the first conductor is connected to the first of the second, like this. This is the second of the first connected to the first of the second. The last plate is connected to the earth. This one is connected to the, this last is connected to the earth. This is the combination of such a type of combination is called as the series combination. The last plate is connected to the earth in series combination. Charge on the plates are the same on each capacitor. Potential difference across the series combination now of capacity V whole. Now we are going to obtain the equation for the capacitance of the capacitor in series combination, like this. Here this is the V1, this one is the potential across this plate first capacitor, this one is the second V2 and this one is the third. Therefore V is equal to Q divided by C1 plus Q divided by C2. These are the equation, that is the basic equation we obtain from our next above equations. Therefore we are going to find out the total capacitance, which is called as the resultant or the equivalent capacitance. That is the V is equal to Q divided by Cs. Now this Cs, therefore this V is equal to, what is the value of this V? V is equal to the potential because of all these capacitors. Therefore, putting this value in this equation, we got the equation, that is the, instead of this V, we can write down the Q divided by Cs. That is the represent this equivalent capacitance. This S, that is the Cs, is nothing but the capacitance or the resultant capacitance of the series combination, which is equal to Q divided by C1 plus Q divided by C2, Q divided by C3. Okay, therefore this Q common, here this Q is common and therefore this Q get cancelled, and finally we get the equation 1 upon this series combination capacitance, which is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. This arrangement can be extended to an equivalent capacitor for n capacitors connected in series, and in this way here we obtain the equation for the 3 capacitors. Similar manner we can obtain the equation for series combination of n number of capacitors, like this, where this 1 upon C equivalent or is indicate the combination of the series. When we rearrange this equation, finally we got the equation, that is the series combination equivalent capacitance is equal to C divided by N, where this N indicate the number of capacitance. In this way we see the series combination of this capacitor. Now see the parallel combination. Now in this combination, these capacitors are arranged one above the another. The insulated plates are connected to common terminal A, which is joined to the source of potential, while the other plates are connected to another common terminal B, which is earth. In this combination, all the capacitors have the same potential difference, but the plates, that is the charges Q1, Q2 on the capacitor first, again this plus or minus Q2 on the capacitor 2 and plus minus Q3 on this capacitor third, and the charge Q is applied at point A. Now see, again similarly we can find out the equivalent capacitance for the parallel combination. For this total charge which is given, that is the Q is equal to Q1 plus Q2 plus Q3. That is the total charge because of these 3 capacitors. Therefore Q is equal to C1 plus C2. That is, we are making this equation in the terms of the capacitance. Okay, C1V plus C2V plus C3V. Let Cp be the equivalent capacitance of the combination. Then this Q is equal to Cp into V. That is, this is Cp is nothing but, again here like SCS, this Cp is nothing but the parallel total or resultant of the combination of this capacitance, which is called as the resultant parallel capacitance. That is the Cp into V is equal to C1V plus C2V plus C3. That is the corresponding values of the capacitance 1, capacitance 2, capacitance 3. Therefore Cp is equal to C1 plus C2 plus C3. The general formula for effective capacitance Cp for parallel combination of n capacitors follow similarly. Here again, like as the series combination, here we got the equation for the parallel combination, that is Cp is equal to C1 plus C2 plus dash dash up to Cn. That means, what is this indicate? That means you can obtain with this formula for n number of capacitors, and like this we can obtain this formula in series. There is the inverse, and in this parallel, C, that is the number of capacitance, which is equal to Nc. In this way we see the how this series and parallel combination of the capacitors. Now see the next concept, which is again related with this capacitance concept, that is the capacitance of a parallel plate capacitor without and with dielectric. Here this capacitor, if the between these two capacitors, if there is any medium, with medium or without medium, how this formula gets changed. Therefore, the capacitance of a parallel plate capacitor without a dielectric, a parallel plate capacitor consists. First of all, we are going to see the case without a dielectric of two thin. Here, this diagram of two thin conducting plates, each of A, that is the A is the area held to each other at a suitable distance. This is the distance, that means nothing but the distance between these two plates is equal to this D. Okay, when a charge positive Q is given to the insulated plate, we know that because of this positive charge, the negative charge induced in the neighboring plate, then this minus Q is induced on the near face of earth plate, and this positive Q is induced on the further face. But at this earth, the charge positive Q being free flows to the earth. In outer region, the electric fields due to the two charged plates cancel out, and this is the main concept. So the next field becomes, that is the E is equal to, this is the sigma divided by 2 epsilon naught minus 2 epsilon naught, which is equal to 0. The inner region, the net field is, inner region, that is the this inner region is equal to sigma divided by 2 epsilon plus sigma divided by 2 epsilon, which is, that is just 2 sigma divided by 2 epsilon. 2 get cancelled. Finally the equation remains this sigma divided by a epsilon. The electric field between the plates is given by, again we know the equation, that is the E is equal to V divided by D, or we can rearrange the equation, that is the V is equal to ED. And here this value of E, which is got from this equation, which is nothing but the sigma divided by A epsilon naught, putting this value in this equation, and finally V is equal to sigma A epsilon naught into D. Capacitance of the parallel plate capacitor is given by, now we have the basic equation for the capacitance, that is the capacitance is equal to Q divided by V, and from this we got the equation for V. Therefore, putting this value of this equation here, Q divided by QD divided by this A epsilon naught, and therefore this Q gets cancelled, and finally we got the value, that is the A epsilon naught divided by D. Now see the next condition, that is the capacitance of a parallel plate capacitor with a dielectric slab between the plates. Here this is the dielectric slab. Consider a parallel plate capacitor with the two plates, each of area A, separated by a distance D with a dielectric slab between the plates. The capacitance of the capacitor is given by, now we have this formula, C naught is equal to A epsilon naught into D. Okay, where this is the dielectric field without dielectric. The potential, where we also got this formula without dielectric, that is the E naught is equal to sigma divided by epsilon naught, which is equal to Q divided by A epsilon naught, where the sigma, the surface charge density on the plates. Again, we have to rearrange this equation. So using this equation, the induced charge set up the field EP, that is the inside the dielectric, in the opposite direction of E naught. the induced field is given by, that is the EP is equal to sigma P divided by E naught. Again we are using this equation, that is the sigma P is equal to QP divided by A. Putting this value, this equation become, that is the QP divided by A epsilon naught. These are the mathematical terms. We are rearranging this basic equation only here. The net field E inside the dielectric reduces to epsilon naught minus EP. Again, therefore, the total field we are going to find here, this E is equal to E naught minus EP. Again, this E naught K, that is the dielectric constant, therefore, rearranging the term E naught divided by E naught P, that is, which is equal to E is equal to Q divided by epsilon naught K, or the Q is equal to A K, that is the dielectric constant epsilon naught E, where this EP exists over a distance D and E naught over the remaining distance. These are the concept. Okay, this E naught and EP. EP exists over a distance T and E naught over the remaining distance, that is D minus T between the capacitor plates, and hence the potential difference between the capacitor plates is become, that is the V is equal to E naught in minus D minus T plus E in, that is the T. Therefore, again rearranging this equation here, this instead of this E, or here you can say epsilon also in your book, epsilon naught K, therefore this common, therefore E is equal to E epsilon naught K, here I written here, therefore epsilon naught become common in bracket D minus T plus T divided by K. Again we know that this E naught is equal to, and putting this value in terms of the charge and area, we got Q divided by epsilon naught, which is equal to D minus T plus T divided by K. The capacitance of the capacitor on the introductions of dielectric slab, the equation becomes like this. Because of this dielectric slab, the equation becomes C is equal to Q upon V. This is our basic equation. Therefore, this Q, and this is nothing but the value of this V, which is because of that dielectric slab. And putting this value in here, in this equation, this Q get cancelled. Again, solving this, we can finally got C is equal to A epsilon naught divided by D minus T plus T divided by K. And this is the final equation, that is the capacitance with the dielectric slabs. Now see the special cases. If the dielectric fills up the entire space, suppose whole space between these plates filled with this dielectric, then what happens? This T is equal to become D. Therefore, C above equation, that is D is equal to become T. Therefore, is equal to only T divided by K. Therefore, final equation, this K goes in upper position. Therefore, final equation become C is equal to epsilon naught K divided by D, which is equal to K into C naught, where this K is equal to C divided by C naught. Capacitance of a parallel plate capacitor increases K times. That means if the capacitor is filled with dielectric slabs of thickness like as T1, T2 up to Tn, then this arrangement is equivalent to the N capacitors connected in series as shown. Like this, only their equation is changes like this. C is equal to A epsilon naught T1 divided by K1, that is we fill, that is the capacitors is filled with the dielectric slabs of thickness T1, T2, like shown in is this diagram. Okay, now the second case is, that is the if the arrangement consists of N capacitors in parallel with the plate areas A1, A2 up to dash dash AN, and plates separated by distance D, then this equation, we are just changing the equation accordance with these special cases. Okay, this is the main equation. With the help of this main equation, we are going to see the what happen if the entire space is filled with the total dielectrics, if the capacitor is filled with the dielectric slabs of the thickness T1, T2 up to T1. And third one is we are going here seeing that the A1, A2, these are the areas. Okay, therefore this is our basic equations going change with these cases. C is equal to A epsilon naught divided by D, where A1K dash dash A2K, like this. Where suppose this A1 is equal to A2 is equal to A, and then finally we got this A divided by N. In this way, this equation gets changes for that condition. If the capacitor is filled with the conducting slab, K is equal to infinity, then C is equal to D minus, that is the D divided by D minus T, which is equal to C naught. Where C is greater than C naught, the capacitance thus increase by the factor T, d divided by d minus dt. In this way, these are the special cases which related with this dielectric slab equation. Now see the next equation or the last concept of this electrostatics. Energy stored in capacitor. How this energy is stored in this capacitor? Consider a capacitance of a capacity C. Then by the being charged by the DC source, here this is the DC source, V holds during the process of charging. Let Q be the charge on the capacitor and V be the potential difference between the plates. And finally we got the equation using this Q and V, that is hence C is equal to Q dash V. A small amount of work is done if a small charge dq is further transferred between the plates. That means we are first taken small charge. Therefore, dw is equal to, that means we are going to find out the first the small work for the charge, small charge dq. Therefore, dw is equal to v into dq. Again, we know what is this V, that is the Q divided by Q dash divided by C. Here we rearrange this equation for V. C is equal to Q dash divided by V. Therefore, the small v is equal to Q dash divided by C. Here we just only rearrange the terms. Therefore, the total work done in transferring the charges, that is the W is equal to, we are going to take integration from 0 to final total charge Q here. Therefore, Q dash divided by C dq. Therefore, which is equal to 1 upon C, that is the integration 0 to Q dash dq. And solving this mathematical term, that is the 1 upon C, Q dash square divided by 2 Q into 0. Therefore, 1/2, that is the here this 1/2 here 1, and this rearranging or solving this mathematical term, the work done is stored as the electrical potential energy U of the capacitor. And this is the last concept of your electrostatics chapter here, that is the work done of this stored in capacitor can be expressed in the terms of forms as a follows, that is the Q is equal to 1/2, that is the Q square divided by C. Therefore, which is rearranging this equation, that is Q is equal to C, CV, therefore 1/2, here CV square, and this equation, that is the here we put this value, and finally we got this equation in three forms, that is U is equal to 1/2 Q square divided by C, which is also equal to 1/2 CV square, and which is also equal to 1/2 QV. And this is the end point of this electrostatics lecture. In next section, we are going to see the electric current. Today we stop here.